Thank you very much for this kind introduction. Of course, there's a bit of pressure here giving an introduction on scattering amplitudes of some of the world experts sitting in the audience, but I'll do my best. Indeed, as Volker mentioned, there's some lecture notes on this topic, but also I saw in the SAGEX curriculum there's a lot of fantastic resources, both introductory material, lecture notes, and also some guides to the original literature, some of which I think is really very readable even at the beginning of studying this topic. So I definitely encourage looking there for further source of material. And of course, I welcome you also to come to me after the lectures if you have questions or want to have some hints what to read up further. Very happy to provide this. So let me just get sorted out. There's some talk.
There's plenty of talk.
There's plenty of talk, great.
I think you see there is not a big box of it there.
Wonderful. You mean this one?
This one should be full.
Okay. Maybe while we're setting up the logistics, let me just ask to get some idea of who's in the audience. Actually, I assume that most of you are PhD students, but perhaps some also in the master's program. So maybe just to get a feeling, I mean, who's a PhD student? Okay, that looks like the majority. Any master students? Okay, that's okay. Sizable number. Postdocs. Right, very good. So I think that fits more or less with what I expected. And just out of curiosity, between locals and people from outside, who's from Hamburg? Okay, and so I guess most of you are from somewhere else. Yes. Okay, so that was a trick to do the morning gymnastics. So I'm woken up. Let me just say my name again is Johannes Henn. I work at the Max Planck Institute for Physics in Munich. And sort of my group we're interested in various topics in scattering amplitudes. So all right, there's some more gymnastics for me to do. So let me just say a few words about what I'm planning to do in these lectures, and also a bit how they're connected to the other lectures in this school. So the title of this lecture course is Introduction to Scattering Amplitudes. So that is scattering amplitudes in quantum field theory of elementary particles, and this naturally. So in quantum field theory, particularly in perturbative quantum field theory, we expand in the coupling. So the natural first step is to discuss the lowest order scattering amplitudes, and that's actually what I'll mostly be talking about, giving some introduction to the basic framework, the notation, and so on, and mainly focusing on the properties of tree-level amplitudes. So as it turns out, first of all, I mean, you might think, perhaps if you haven't been introduced to this topic, that this is something rather boring and trivial. But so first of all, let me say that it's actually a quite complicated problem. Somebody asks you to please compute a scattering amplitude of 8 external gluons. If you think about the traditional way of starting to write down Feynman diagrams, think about computing them one by one, it actually turns out to be rather, or actually very complicated. And on the other hand, often we find that results are extremely simple and compact if one thinks about them in the right way. And so this process of going from something that is in principle understood but very complicated to having some very beautiful and nice answers, this helps finding some good ways of thinking about these calculations. And in fact, many techniques or new ideas have come about have their roots really in properties of tree-level amplitudes. And so then these techniques, there's various examples where understanding something at tree level helps you also understand some more complicated problems at loop level. For example, and this we'll hear about in David Kosso's lecture, for example, how about organizing the loop level integrands, performing similar simplifications at the integrand level, but then also, and this will be a topic of Claude Dour's talk, how that connects to the special functions, logarithms, dilogarithms, and so on, that you encounter when you evaluate these loop integrals. So although this is in a way rather basic, it connects to these really complicated and up-to-date research topics. So as I said, so that's connected also to loop level amplitudes. So this will not be in my lecture, but it's connected, as I said, to these other lectures. So where, roughly speaking, there's questions about integrands. Of course, I'm oversimplifying here, but so this is one topic that David will discuss. And then the special functions that arise when you carry out the loop integrations. So that's an aspect of Claude Dour's lecture series. And as I said, there's important interconnections. If we have time at the end, I might say a few words actually about this, but I think for the most part this will be in these 2 other lectures. An important aspect in seeing simplicity is to think about symmetries. So this is something that I'll discuss. So it turns out that sometimes just thinking about what are the underlying symmetry properties of amplitudes helps you in understanding their properties and seeing some simplicity. And this includes both obvious symmetries, so symmetries that you can see at the Lagrangian level, but there's also new and hidden symmetries that are a bit surprising. So again, I definitely cover the first part, and perhaps if there's time also the second. At any rate, this will then be connected to another topic, which is so going into the direction of theories that have more supersymmetries. So in fact, all I mentioned here, this is applicable in principle to any QFT, so including QCD and the standard model. But it turns out it can be very profitable to look at if you wish, toy or textbook theories. And if you go into the realm of supersymmetric theories, then there's the topic of so-called ADS CFT and holography, which will be covered by Gleb in his lectures. Gleb Aritunov, I don't spell his last name because I'm a bit unsure now of getting the letters right, so please forgive me for that. So as I said, that is also closely connected, and it turns out that often looking at some kind of more supersymmetric toy models really helps in understanding the key structures that then also inspire again the work in QCD. So I think this is really a nice, nicely all interconnected. And now finally along the same lines, going beyond string theory, let's see this ADS. There's also interesting connections to string amplitudes. And again, this is a topic where a lot of insights have come or have been understood between field theory and string theory, even at tree level. And so this will be covered by Oliver Schlotterer. All right, so I think this gives you some kind of an overview of what to expect in this school. Now I should also say what I don't cover. So I said that we were discussing scattering amplitudes of elementary particles. So like gluons, electrons, quarks. Now, of course, in an experiment, in particular in hadron collisions, we don't scatter directly gluons, and also we don't measure them directly. So I think this is important to understand that what we are computing here is an ingredient, an important ingredient that helps to make the connection to experiment. But it's not the only step. So there's a whole chain of things that one has to know. And I'd just like to give you a picture of this. Probably you've seen this. So if you scatter protons, so let's say they come in here, we have their constituents. Typically what happens is that what's actually scattered is in this proton, out of this proton, some of its constituent, which could be a quark or gluon. So there's some story of Parton distribution functions here. And so the rest of the proton goes on here, and similarly of the second one. So we have some picture like this. And so these, as I said, these could be quarks or gluons, and so when we talk of scattering amplitudes, what we can calculate in perturbation theory is the scattering process of these elementary particles. So now here's some interaction, which could be represented by Feynman diagrams. I just put it as some blob here. So this will be the perturbative S matrix. And then out of this, you could have some other particles coming out, like, for instance, some gluons or something else. And so it's this piece here that I'll be discussing in the lectures, how to compute the scattering amplitudes, in other words, the probability for some process to happen. And so then finally, also it's not the gluons that are measured in the detector, but then there's another story of what happens when a gluon is produced and how that forms a jet of particles which are then finally detected. So then this, here there's some jets of particles that are actually measured. So this is just to give you a picture of how this works on amplitudes, how it's related to collider physics. And although I don't think this will be explored more in the lectures, of course, if you want to know more, I think David Kossler certainly is the right person to ask more about this. All right. So any questions so far about this overview and what we're planning to do in these lectures? All right. And let's get started. So I wanted to begin picking up on this idea of simplicity and how it can be that although we have a very complicated problem of summing over many diagrams, the end result can sometimes be very simple. So I'd like to start with a preview of that. For that, I'll just introduce a little bit of notation, and then having given you this preview, I'll go and build things up a bit more systematically. But let's start with this. So let's start with some example of simplicity. So I want to consider scattering of gluons. So gluons are massless particles that have spin 1. So first I need to introduce some notation. So let's say we have some, we denote the scattering process as a blob like this. So this blob should represent basically all Feynman diagrams that we can draw. And here we want to consider only tree level diagrams. So I put some dots here because this could be an arbitrary number of particles. So what could this be? So these are diagrams that look like so. Etc. Depending on the number of gluons. And of course, there's many more such diagrams. Now, what do we need to specify what exactly it is we're doing? So first of all, I said that the gluons have spin 1. Being massless particles, they can be classified by the helicity, which is projection of the spin along their momentum. And so gluons can have helicity +1 or -1. So they're labeled by helicity. So plus or -1 for each of the external gluons. And by the momenta, they depend on the momenta pi. I running from 1 to n. There's actually also color, because they are joint particles in SUN, but that actually I'll discuss a little bit later. So for now, I'd just like to get to a stage where I can present to you some sample formula. So the only thing that I need to tell you is how we deal with these momenta. So I said the gluons are massless. Because of this, they satisfy some constraints. So the square of a momenta is 0. So this is for any I. Also, they satisfy momentum conservation. But what I wanted to focus on is this. And so there exists a very convenient formalism for dealing with massless particles in 4 dimensions, and that's the so-called spinor helicity formalism. So what one does is one takes the momentum p mu, and first of all one can write this equivalently in the following way. So here it's a momentum in 4 space-time dimensions. So this vector has 4 components, but one can rewrite it in the following way with the help of some sigma matrix. One can write it in terms of some other quantity, which is a 2x2 matrix. 2x2 matrix. So in this way, if you wish, this is just a different organization of the same information. Instead of a 4 vector, you have a 2x2 matrix. Now, thanks to this, we can ask what does this masslessness condition mean for this matrix. And so it turns out that in general, this means that one can write this matrix in a factorized form, introducing some new objects, lambda and lambda tilde. So these are two component spins. Now you could observe that I've in a way you could say that I've cheated a little bit, because we started with 4 degrees of freedom, and I told you that the solution of this masslessness condition is to write the matrix in this factorized form. But now it looks like we still have 4 degrees of freedom, right? Because each of these lambda and lambda tildes have 2 components. So there's something a bit funny here, and but in fact it's the following, that writing this product, we've introduced a redundancy, and the redundancy is that we can simultaneously rescale lambda and lambda tilde. So if I rescale lambda by some number and lambda tilde by its inverse, then this rescaling drops out. So in fact there's only 3 degrees of freedom, and there's simply a redundancy. If you wish, you could call it a symmetry, but I prefer to call it a redundancy. So in reality there are only 3 degrees of freedom in it. So there's a redundancy, rescaling. Let's see. So you could take lambda and rescale it by some number, complex number, and similarly for lambda tilde. And this definition would stay invariant. Okay, now you might be a bit surprised by why are we doing this? Isn't this a bit strange? I guess it's one can really justify it a posteriori why this is a nice thing to do, and actually you see momentarily that at least for the example I'm giving you, this is really a very good idea. So now we have these lambda and lambda tildes. So now the idea is that any quantity that arises when we evaluate Feynman diagrams such as this one, we rewrite it in that notation. And so what quantities do we usually have to deal with? Well, we have Lorentz invariants. So the question we can ask is what kind of Lorentz invariants can we build from these lambdas and lambda tildes? Well, and this is a bit like with momenta. I mean, you know very well what invariants you can build there. Basically, you take scalar products, and then you're guaranteed to have a Lorentz invariant. So similarly, here with the lambdas, so we build Lorentz invariants. I found a better choke. Nice. So we can build Lorentz invariants by contracting indices. So, for instance, we can take the lambdas, any two lambdas, and contract them with the antisymmetric tensor in 2 dimensions. And this we will denote in some shorthand notation just as Ij. And similarly for the lambda tildes, we'll use this square bracket notation. And so, as I said, this is an antisymmetric matrix. So in fact, in components, this would be just lambda I1, lambda J2 minus lambda I2, lambda J1. And similarly here. So when, for example, if you had a scalar product of momenta, for example, pi dot pj, then this can be immediately rewritten in terms of these lambdas. So this is just ij, and in my conventions, and I think conventions quite commonly used, this is then written like this. I should say I'm in these lectures I do my best to get all the factors of -1 and I and so on correct, but I will most certainly fail. So my general advice for you is to whenever when you do your own calculations to really make sure that you have a set of conventions that you've checked and that you kind of consistently compare that in your calculation everything is that there's no other way than just to do the calculations and to make sure that one has a consistent set of conventions. But as I said, I'll do my best, but it's since sometimes one takes formulas from various sources, it's a bit difficult in these lectures. But anyway, so this is how you would rewrite the momenta, the scalar products of momenta. So what you can see is that in some sense, the spinors allow you to take they're a bit like square roots of the momenta. And later on, we'll see that when we discuss singularities of Scattering amplitudes, you might expect on general grounds that there are singularities when something special happens to the momenta. For instance, when a scalar product like this vanishes, and this is indeed the case. It will turn out, however, that it's actually to describe these singularities, it would be much more convenient to use these lambdas or lambda tildes. So if you wish, this is a posteriori is one motivation why it's a good idea to use these variables. But now, So now I think after having gone through this bit of notation, now we're in a position to see a first nice scattering amplitude, and I guess I write it up there. So let's write down the so-called MHV amplitude for scattering of n gluons. So first I should explain what does this MHV mean. So this refers to the helicity. So since the gluons can be labeled by either plus or minus helicity, this gives us a way of classifying them, and it kind of makes sense to start with the simplest amplitudes and then move on to the more complicated ones. It turns out that there's certain amplitudes, namely the ones with just all equal helicity, so all plus or all minus, that they're the simplest types because they just vanish. So we can show that they're zero. We'll see later an argument based on supersymmetry, which kind of very cleanly allows you to show this. But for now, I just posit it here. And actually, in the same way, when you have an amplitude with all plus helicity gluons and just a single minus helicity gluon, similarly they vanish. So this is at tree level, and there's an elegant way of showing this by supersymmetry. Also, if you wish, it's possible to think about the Feynman diagrams and think about what happens when you contract these Feynman diagrams with polarization vectors that correspond to these plus and minus helicities. And also in this way, one can also show this more directly. I believe there's some DESY lecture notes by Lance Dixon where this is spelled out. So if you're interested, please do have a look there. So now what did we just see? So if we have these scattering amplitudes, all plus helicity, these are zero, and the ones with a single negative helicity gluon, they're also zero. Now I'd like to explain this name, which I haven't said what actually MHV stands for, but I'd like to motivate it now. So I haven't said it earlier, but we're in a convention just for simplicity, where we consider all gluons outgoing. So this means that it's like a process where you have nothing. Sorry, nothing. So the zero stands for nothing, vacuum, and you generate all these plus helicity gluons, right, with outgoing momentum. Now, equivalently, and this is of course from the point of view of a scattering process is more natural, is to say, okay, I have a certain number of gluons that are ingoing and a certain number of gluons that are outgoing, right? And but in this way, when we flip the direction of the momentum, we also flip the helicity. So it's equivalent to saying It's equivalent to saying, well, we have a bunch of ingoing particles here and a bunch of outgoing particles here. It doesn't have to be necessarily the same number. So outgoing ones still have this plus helicity convention, but the ingoing ones now have this negative helicity. Have negative helicity because we flip the direction of the momentum. So in this sense, now if you look at such an amplitude, what happens is all the ingoing gluons have the same helicity, all the outgoing ones have the same helicity, and so, but it's a differing one. So helicity has been flipped, and you could say in a maximal way. So one could say these are the maximally helicity violating amplitudes. As opposed to amplitudes that conserve helicity, right? So this is just a name. Now, I just told you that actually the maximally helicity violating amplitudes, they're zero at tree level. And likewise also if you wish, the next to maximally helicity violating amplitudes are also zero. So just for that reason, since those are zero, this name of maximal helicity violating amplitudes, it shifted a bit, and it's used, in fact, for the amplitudes where you have all helicities plus except for 2. Because this turns out to be the first helicity amplitude that is non-zero at tree level. So if you wish, it's a bit of a strange convention, but that's how it, I guess it came about. So this is why MHV amplitudes refers to the case where you have all helicities plus, and then say at position I, a negative helicity gluon, and then at some other position J, another negative helicity gluon, and so on. Okay. I should say perhaps just for reference that I should emphasize that this is true at tree level. At loop level, these amplitudes are in general non-zero, and so therefore, then at loop level, it's a bit strange to use this naming of MHV and so on. But okay, I guess you understand where it comes from. So. All right, so now I've introduced the naming, and now we're in a position to give a first example. So I've talked a bit about how complicated it seems actually to compute, say, an 8 or 9 gluon scattering amplitude. But now there's actually something extremely remarkable. We've already seen 2 exact formulas that apply for an arbitrary number n of gluons. And now we're going to see a further example. This time it has a bit more meat to it, so to speak. It's actually not zero, but one can just give a closed form formula for this MHV amplitude at tree level. And so let's just denote this by AN and denote the positions of the negative helicity gluons. So this amplitude, in fact, turns out that it's given by the following formula. There's an I, which is the just for the imaginary part. If you keep track of the coupling, there's a factor of g to the n minus 2. It comes from these free gluon confinement rules. And then it's given by the following formula. So there's upstairs the ij to the 4. And downstairs we have a string of these angle brackets, 1, 2, 2, 3, and so on. And goes on until n minus 1, n, and then there's a final factor of n. So this is the tree level amplitude for scattering of n gluons with all plus helicity except for gluon I and J that have negative helicity. And it's just given by such a simple one-line formula. This is the so-called Taylor formula from, was in fact found in 1986. So a few years ago there was the 30th anniversary of this wonderful formula. So I'm just looking at the time. when should be the first break or feedback session?
So, as we said, yes, normally the lecture should take 1 hour, so up to 10:30, plus 15 minutes of questions or discussion. But okay, we are a bit flexible with but not too much.
Not too much. Very good to know. Okay. So here it says we have until 10:45, and so toward the end we can do this question session. Of course, maybe this is now also a good moment that we have our first example of a nice formula. If you have any questions about that. Yes.
The question: to which theory is now this applies to?
Yeah, great. That's a great question. Thanks. So this is the formula for scattering of n gluons, right? So this is literally all diagrams that you can produce of the well-known Feynman rules for Young-Mills theory. So you have a 3-gluon vertex, 4-gluon vertex. It really says that for any number, whatever n is, you're supposed to draw all the tree-level diagrams, sum them up, project with these polarizations, and get this answer. Now, you asked about how can it be that if we're looking at Young-Mills theory, how can there be a SUSY argument? And indeed, this is a bit surprising, perhaps. But it's so this is there's actually a nice explanation. Namely, when you're at tree level, you can think how different is it actually consider an amplitude for gluon scattering in a supersymmetric theory or just in pure Young-Mills? What would actually be the difference, right? And so this you can think about it at a diagrammatic level. So what changes if we have a SUSY theory? So what could happen in the SUSY theory is that you might have some new particles like scalars, right? You might have some phi bar that can couple to the gluon in a canonical way, or even then through the commutator in this way. You might have further particles, some fermions that then in turn couple to the scalars. Let's say psi, something like this. And in general, a host of more interactions, which are all related by supersymmetry. Now the point is, when we consider scattering of gluons, yes, we could have terms like this, where we produce some of these SUSY partners. However, if they're not in the external states, it means that they would have to again disappear in some way. And the only way this can happen is that if they form a loop. So, in other words, as long as we're staying at tree level, it in fact does not matter if we're talking about supersymmetric theory, Young-Mills theory. The Feynman diagrams is just exactly the same. So, this means that we can just, if we wish, we can just use SUSY arguments to discuss. We can consider the gluon amplitudes to be, if you wish, embedded in some SUSY multiplet. But this gives us a huge advantage because then we can use this extended symmetry group to make some predictions. And as I said, in this particular case, it allows you, through relating these gluon amplitudes to some other component amplitudes, allows you to actually show that they're related to something that vanishes and therefore need to vanish themselves. So thanks for the question. Any other questions at this point?
So there cannot be two gluons, one scalar, or two gluons, another type of particle that comes from supersymmetry, right?
So they are, right. So the statement is that if all external particles are gluons, then as a consequence also all the internal ones need to be gluons at tree level. Otherwise the only way to produce a graph would be at loop level. So at loop level, yes, you could have something where you have some scalars like this, and then you could form a graph, and this would clearly be something that you don't have in Young-Mills theory. But in fact, there's still some mileage you could get out of this. You could say, well, I take this and I combine it with my Young-Mills graph, let's make this a fermion, for instance. And you could say, oh, but this sum, if I take the fermion in a certain representation, and also a joint representation, I could make this to be a graph in an n=1 supersymmetric theory. And then I can say something about this amplitude. And then typically what it could buy you is that you can say, well, the gluons are a bit complicated. I prefer to, through this SUSY insight, I prefer to relate this one-loop gluon graph to the one-loop graph with just the scalar loop inside. So this would be a very direct way of making some use of SUSY. By saying, well, I know something about, or for some reason the SUSY theory is simpler, I have a SUSY result, and then I use that to trade the complicated gluon graphs for some graph of scalars. So this is something that's actually been done in the literature. It's called supersymmetric decomposition. In fact, there exist some more refined versions of this. And it's certainly very helpful. Personally, I like to think of these explorations of SUSY amplitudes and also amplitudes and ideas coming from string theory in a slightly different sense. Because this is really kind of very direct, but I think there's a whole set of ideas which are a bit less direct, but potentially much more useful, where you understand some simple structures by studying the SUSY models, or you see a dual formulation inspired by string theory, and it gives you something that you would not have thought about directly just by doing a small perturbation like this. So I believe there's two ways of using supersymmetry. One way is very direct, as we're seeing here by the identities, word identities. But another way, and I believe perhaps much more interesting, is that these theories sometimes will organize perturbation theory in a completely different way. And in this sense, give you a completely new approach to thinking about the amplitudes. Yeah.
So does there exist a generalization in this program to the others?
Yeah, so I just mentioned some concrete way you can do this at one loop order. So I think this would be called SUSY supersymmetric decomposition. Maybe let me just write roughly what the idea is. So you have the amplitudes. So this is again for external gluons. So you have a full amplitude, and well, roughly speaking, it's linear algebra, right? So what do we have? So here we have the gluons, as I said. And this is the thing that you don't want because it's the most complicated one. So you seek to re-express it in terms of simpler things. And so what could it be? So first of all, you can write down some amplitudes which are supersymmetric. So you could say, well, I want actually, it turns out the maximal amount of supersymmetry in 4 dimensions is some n=4 supersymmetric theory. So you can say, well, I re-express part of it as some, in that theory, I have an n=4 supersymmetric particle running through a loop. So that's something that involves scalars and fermions in a particular way. But okay, you didn't have those scalars and fermions in the first place, so you need to get rid of them. So then another thing you can do is you take an n=1 multiple. So that's actually what I just had there on the blackboard. So that's also okay because it's a bit simpler. And then finally we need one more object, and that would be that you can choose to be the one where you just have the scalar particle, scalar in the loop. And so in this way, in general, when you have the one loop graph, you can trade the gluons for these 3 pieces. And it can be, as I said, it can be advantageous because first of all, if you just think about Feynman diagrams, it's nicer to just have scalars than gluons because they have lots of derivatives. And then these two are supersymmetric, so you can hope that they're simpler for some other reasons. Or indeed, if you look at some special density configurations, they just simply vanish. So this is Derek Bay. Now I forgot where the question came from. Oh, from up there, yes. so does this answer your question? I think there's also some more technology at multi-loop when looking at so-called unitarity cuts of keeping track of what particles flow in the loop. I don't know, David, is that, will you comment on that? Probably not. Well, if not, then there's some references we could give. Yeah, that's one way of doing it. All right. So now let's see. Next. Okay, I think since I'm sure this spinor-Listi formalism is a bit unusual, and I mean, my idea was now to just expose you briefly to it. I'd like to just end by giving you a few more properties so that you're a bit more familiar with these spinors. Maybe can I just ask who has seen these lambdas and lambda tildes before? Is that, okay, so maybe I should not worry too much about that. All right. Okay. Does everyone know what a Schouten identity is? So if you know, maybe. Okay, so I think that's maybe a third, and another third was too lazy to raise the arm. But I think for the benefit of the other third, I'll say a few words, right? Some spinor gymnastics now. Okay, just leave a slide on the right. So first about the Listi with I've already used this, but I just want to say very clearly that in a way we've made a convention of what we call plus Listi and what we call minus Listi. So let's formalize this a little bit. So we have this convention that to lambda we assign so a convention for the Listi. So the convention is that to lambda we assign Listi minus 1/2, and to lambda twiddle we assign Listi plus 1/2. So let's just see how this works in the case of the MHV formula up there. So we have I and j to the 4th power upstairs. So 4 times minus 1/2, that's minus 2. But on the other hand, we have this string of brackets downstairs where every gluon appears once. Appears twice. So that subtracts 1. So we end up with minus 1. So Listi minus 1 for I and j. And likewise for all the other particles, they appear downstairs 2 times. So that's that's minus 1, but since we're downstairs, it flip the sign, so that comes to plus 1. So that justifies the Listi assignment that we had up there. So this is just I mean, it seems a bit silly perhaps, but when you do practical calculations, it can be just a very, very basic sanity check that your expression kind of makes sense, just to check that the Listi weights in each term are consistent. So also if you, let's say you look at a formula in some paper and it has 3 terms. If you're a bit unsure about what they mean, I mean, it's a very good thing to do just to see, okay, did they get the helicity right? Does it make sense at all? And then if yes, you continue. So this is useful. Now later we're going to discuss symmetry. So I'd like to also introduce some generator that formalizes a little bit, that measures the helicity. So we can have an infinitesimal generator, the helicity operator, which just implements what this convention that I said. So we take it to be 1/2, and we have minus lambda d by d lambda, plus lambda twiddle, alpha dot d by d lambda twiddle, alpha dot. So this is just an operator which if it sees any lambda, well, it just detects it and gives you minus 1/2, and if it sees any lambda twiddle, it gives you 1/2, and otherwise just reproduces the expression. And so this is an infinitesimal generator, and this is the infinitesimal generator. If you exponentiate, it generates this rescaling that we talked about earlier. So remember, there was this ambiguity in rescaling lambda and lambda twiddle. So this generates the rescaling that I talked about earlier. So lambda goes to some factor. If you think of it as a yes, but actually it generates a phase that corresponds to this rescaling. Yes, so so this is just to make sure that we have the same convention about helicity. Now, one other important point is a practical point how to work with the lambdas and lambda tildes. So our starting point was an amplitude that depended on n momenta. We now shifted to these new variables. The original momenta, they satisfied some constraint. They had the mass test constraint and also the momentum conservation constraint. This is for all outgoing. Now things have improved a little bit because we've solved explicitly this constraint here, right? So we don't have to worry about it anymore. So this is solved by using lambda twiddle, but we still have that constraint over here. So this we need to keep in mind. And related to this, the other point is that you can ask what in general are independent variables to describe our scattering amplitudes. And in fact, these spinor products that we introduced, the ij angle bracket, ij square bracket, they're in general not independent. And so this means that in principle it can happen that you find some expression for an amplitude, you express it in terms of those variables, and someone else computes it also, and they get a different formula. But it can happen that the two formulas are equivalent, but it's not at all obvious. And so I'd like to just show you a few examples of how this can happen, and how one, what one can try to do about it. So in fact, the spinors are not independent, they satisfy various identities. And if you wish, the very basic one is the following. Satisfy the cyclic identity. This is called the Schouten identity. It's very easy to remember because you just need to write angle bracket 1, 2, number 3, and then to get the rest, you just cycle around the indices. So 3, 1, lambda 2 plus 2 for each lambda 1 is equal to 0. Why does this hold? Maybe I can ask it to the audience. Can someone tell me why this identity should hold? Sure.
Spinners are two-component objects, so you can have three linearly independent two-component objects.
That's absolutely right, yes. So spinners only have two components, and here we have three different such spinners, so necessarily there's a linear dependence between them. It turns out that this is the dependence, and you could so that's just the case, and yes. So for instance, what you could do to check this equation is you could imagine projecting this with some other spinner, or rather, well, if, again, I mean, since these are basically one way to use that these are two-component spinners is actually just to write out what this is in components, and you just find that it's satisfied. But yes, so the basic reason why this exists is exactly what you said. There you go. So this, well, this seems rather innocent, but then, as I said, can have many consequences. Particularly when you have few external particles. This, this really allows for a lot of different ways, sometimes rather surprising ways of rewriting the same formula. And similarly, now you have momentum conservation. So we can just see what this does. So if we write down momentum conservation, and this is really very useful in practice. So we have just that the sum from 1 to n lambda I alpha lambda I tilde alpha dot, that this is 0. Now, just like in the argument before, it's useful to realize that these have two components. So actually, this equation it has four components. In other words, we can project this with any spinner lambda and any spinner lambda tilde that we want. So in other words, we could write it in the following way: sum from over I from 1 to n, and then now use this bracket notation. Let's say we project with some lambda I, lambda a, where a is any index, and some lambda tilde b. Then this identity has to hold. And maybe just finish by giving a very simple example. So if you have four particles, then let's say for example A we take 1 and B we take 2. Then because of the antisymmetry of these brackets, I cannot be 1 and cannot be 2, so I just runs over 3 and 4. So then it tells you that 1, 3, 3, 2 plus 1, 4, 4, 2 is equal to 0. Again, this is not true in general, but it's true for four-particle kinematics. All right. So I think later on we'll have some exercises where we see some explicit four-particle amplitudes, and we can use that. In fact, I think I can. With what you know, I can already give you some nice exercise to try this out. So let me finish by giving you this example. So I'd like you to use this on some of these amplitudes that I've shown you. So let's take for n equals the n equals 4 MHV amplitude. And let's say we take it just for simplicity. We take the one where we have 1 minus, 2 minus, 3 plus, 4 plus. So let's just write this up. So we have the overall I, and then we have 1, 2 to the 4, 1, 2 to 3. Of course, this cancels if you want. 3, 4, 4, 1. So what is this? So it's this the amplitude with all outgoing. 1 minus, 2 minus, 3 plus, 3 plus. Now, this amplitude should be related to the amplitude where we flip all helicities, right? I mean, we could just perform a parity transformation, and then we'd end up with so flipping all the momenta to the negative momenta. In this way, we flip minus and plus helicities. So this should be related to the amplitude where we have 1 plus. Sorry, what I want to say. Sorry, no, that's not what I want to say. Okay. Sorry, I was about to go into dead end, so let me back out of it. What I do want to say is that you can think about parity, and you might notice that in this amplitude we have 2 negative helicity gluons and 2 plus helicity gluons. So in a way, it's a bit strange that this formula seems to prefer the negative helicity. How to say? It prefers to the lambdas over lambda tildes. But if you think about this amplitude, in a way, everything we did was symmetric, and we could have could imagine using a formalism or way of approaching this where everything is based on the plus helicity gluons. So in this sense, there should be some symmetry between interchanging 1, 2, and 3, 4. And so this justifies that there should be a similar formula which you could call an MHV bar formula. So far we've looked at MHV where we count where we have 2, so it's all plus, and 2 negative helicity gluons. But by parity, we could relate it to something we could call MHV bar. We have all negative helicity gluons and 2 plus helicity gluons. And so in this case, for n equals 4, MHV is MHV bar. So if you think about MHV bar, then we should have an alternative version of this formula, which looks like this. So we can have I, and then 3, 4 to the 4, 1, 2, 2, 3, 3, 4, 4, 1. And now the claim is these two formulas, possibly up to a sign, they're equivalent. And to show this, all you need is on the blackboard. So you will need the Schaltman entities like this one, and the use of momentum conservation like over there. All right. So I think I'd just like to end with this example, and then continue after the break. Thank you very much. So any further questions at this point?
So you had the scaling by A, and then when you exponentiated the generators, you got this EPI5. So A is a complex number, any complex number, and
Yeah, in the rescaling, yes. So the definition is invariant invariant on the value. Yes.
so then each guy file only has like 1, is that?
Yes, I also got confused about that. Any comments from David up there? Well, I think the question was that the LISTI generator it generates a phase, but it's just a phase. And earlier in the definition of lambda and lambda twiddle, one could rescale them by any real number different from 1. So that's just a freedom in the definition, but it's not generated by the LISTI generator. But I mean, yeah, it's just a different thing.
Is A real?
Oh, okay. Yeah. So that's a very good point. A very good question. So the short answer is it depends. So we'll come back to this. In what we've been discussing so far, I mean, obviously to have interactions in four space-time Minkowski space, I mean, these are momenta are just real momentum. Later on, and in fact the next lecture, it will turn out to be very useful to think about a more general setup where you think of a momenta as being complex, at least at intermediate stages. And so in this sense, one always has to, depends a bit on the specific argument or specific calculation that one wants to do. Yeah, so thanks for that question.
So now it looks like if neighboring gluons become collinear, then the amplitude diverges, which is kind of obvious. But if non-neighboring gluons become collinear, it should diverge as well. This doesn't seem obvious from the Park-Taylor form. That's it.
Right. That's a good point. And I've hidden something under the carpet, or not really the carpet, but I've postponed it. We'll see in the second lecture. In the organization of the amplitude, there's a step where one deals with the color information, and I haven't discussed that yet. So this is actually it's the amplitude. It's essential information about the amplitude, but it gives you basically one color structure where you have some cyclic ordering of the gluons. And this explains exactly as you say that here in this formula you see only the singularities for neighboring gluons and not for other ones. But these other ones, they are there. They correspond to other terms in the formula. So roughly speaking, the full amplitude is this formula plus other terms of non-cyclic permutations.
So when these expressions become quite complicated, for instance, higher point amplitudes, what are some good ways of checking whether the results that you have are...
Yeah, very good. So there's in my mind there's two steps. First of all, here these expressions that we deal with, they have helicity. Earlier we made sure that they had the right helicity. So in such a situation, in my experience, it's always a useful thing to kind of pull out an overall factor which takes care of that helicity. So basically you write down anything reasonably simple that has the correct helicity properties. So make sure that at all the points the helicity is respected. You pull that out, and in that way you know that what remains is invariant, is helicity invariant. So and then in that situation you can count how many independent variables there should be, and also make a specific choice of independent variables. So that then I guess I don't know how explicitly we'll see it, but basically it's easier to compare helicity-free expressions where you can go to an independent number of variables. In practice, in my mind, it's of course very useful. First, there's kind of two steps in checking something. First, you need to find the expression that you want to check. And so to do that, it's very useful to replace the kinematics by some numbers. So concretely, you choose, let's say, random components of the spinners, and you check rational expressions. Of course, that's a sanity check. If you want to prove things mathematically, then you can either do what I just said, go to the independent variables, and then just have two expressions that are the same. You could even go in this numerical direction. Sometimes, when I say numerics, it's rational numbers, right? So these are identities between rational numbers. If you do that often enough, in some situations you can argue that you've proven an identity. So a simple example is if you have a polynomial in a variable x, you know the maximal degree, it's sufficient to substitute any identity like p plus 1 times, if p is the highest degree, and then you know you've proven the identity. Likewise, when we deal with rational functions, you could make sure that you pull out all the denominators like there, and you just have something which is then polynomial in the different lambdas. And then again, if you substitute often enough, then you can prove an identity. Maybe just a final comment along these lines. There's something very fashionable and important at the moment, which is some refinement of this idea, which is finite field methods, where you not only substitute rational numbers, but you compute modulo some integer, just to simplify the calculations, and then in this way reconstruct later an identity.
So yes, Johannes pointed out very clearly that with Spinor-Helisti formalism, usually there are very many identities if one insists on expressing everything in terms of the Spinor bracket. And you pointed out a few of the most important identities having to do with momentum conservation and then linear independence. So yes, for n particle scattering, massless particle, indeed you have 3 degrees of freedom, as you pointed out, yes, for each particle, so 3n. And you also have minus 10 for the Lorentz group, that they are equivalent by Lorentz invariance. So for the momenta, we usually know how to solve this by picking a particular reference frame. We are dealing with momenta, and this takes care of everything, of this additional redundancy. Can one think of something analogous when thinking directly in terms of Spinor-Helisti variables, or does one necessarily have to go through the step of starting with the momenta, picking a reference frame, and so on, in order to resolve all these kinds of redundancy due to Lorentz symmetry?
Okay, I think let me see if I understand the question. So I think you want to use the obvious symmetries to kind of get rid of some of these redundancies and basically fix a frame where the number of variables is exactly the right one, and also importantly independent unconstrained variables. Yes, and so this is absolutely this is certainly possible. I mean, it may not. I don't think there's a unique way of doing that, but in for practical purposes, that's certainly a good idea. So the first thing to say is that we went only halfway in the first sense, because we solved the Oncherness conditions in this way, but we still have the momentum conservation, and so which is here. And so the lambdas are not unconstrained variables. In other words, we cannot just take all the, let's say for 4-particle scattering, we can't just take lambda 1, lambda 2, lambda 3, lambda 4 and substitute any numbers. And these have to be still numbers that satisfy these identities. And of course that can be a bit annoying. Now there actually exists another set of variables which is a refinement of this, if you wish. You can go from these lambdas to so-called twister variables, and actually in particular there's so-called momentum twister variables. Momentum twisters. We basically start from these lambdas, but then there's some non-trivial step where you exchange these lambda tildes for some other variables. But the upshot is that these momentum twister variables, you have you have both of these desired properties. You manifestly solve the on-shell conditions, but you also solve the momentum conservation condition. So when these momentum twistor variables, they're completely unconstrained. And in most variables, then, therefore, you can just, you're free to choose any values. And now, moreover, people have done exactly what you mentioned for the case of holistic free expressions. There's even some examples in the literature where, for, let's say, for 4-particle scattering, you can choose momentum twistors with certain components, which you could call X or something like that, and in this way, X and Y, let's say, and it precisely encodes the independent variables. So I think you could find this explicitly for 4, 5, 6-particle scattering, or I think some of our colleagues have also written some codes which give you some independent kinematics for n-particle scattering, and this could be very useful also in the